Okay, thanks. In fact, EU is talking about 300-400 gigawatt within 2050, and already in 2040, they are talking about offshore wind being the most important contribution to the electricity system, and that was prior to the war in Ukraine. So that we cannot handle without a lot of floating offshore wind. We have not areas in less than 30, 40, 50 meters for bottom fixed. And you have identified a lot of interesting questions that has to be addressed to do that, and to reduce cost and to make this reliable source of energy. So, as you have seen here, there are 4 papers and a summary, extended summary of about 100 pages. So it's a lot of interesting things here. And as you state, it's really a multidisciplinary system. And for historical reasons, we know that the rotor nacelle assembly is really coming from land, the land industry. The tower is coming from land industry. And then the floater is kind of coming from the marine industry. So one very general question then is, from what you see, how should an ideal integrated solution be? Not this kind of mixture of a land-based and marine. Should we have a marine floater and a land tower, or should we do something different? Should we have a completely different design?
Yes, actually, we start to see other structures now. For example, have this Bruno. There's one structure that you no longer have a tower. You have actually a truss, and it's sort of triangle structure on top of a semi-submersible. So I think the industry is now starting to think that maybe it's not the case to have a tower moving back and forth with waves, and so I think this is one example, but yeah, I think combinations of trusses and structures that will have less stress at the tower of the base will probably be the next step.
And then you really trigger the next question, and that is, you present fatigue analysis and ultimate plummet state analysis. But from the kind of standards and limits you see here, how will you reflect upon the status of the kind of ultimate probability of failure? That has been maybe adopted a lot from the offshore industry.
Yes.
But what should the criteria be?
Yeah. Well, the methodology, even if it comes from offshore industry, it's quite general. Maybe what might be a bit questionable is the assumption of the distributions that you use, the fractals that you assume, the number of realizations that you use. But I think otherwise, the idea of getting, for example, different realizations and fitting them to distribution and find the probability of failure, that sounds a bit general, at least in principle for me.
Just to follow up on that, in the offshore oil and gas industry, you normally produce one unit. And if it's a systematic error or a random error, well, that doesn't really matter. But when you are making a wind farm with 100, 200 units,
sure,
how will that, what kind of consequences will that have for your design procedures?
Yeah, so then thinking of that, then I would go for more strict requirements in avoiding these possible errors, possible mistakes, possible failed assumptions that they take. Yeah, it's hard to respond.
Yeah. Okay, another thing you are saying is and arguing for is that we have bigger and bigger rotors, and the capacity factor is increasing. But it's really capacity factor. It's used a lot. People are bragging about their high capacity factor, but is it really a good measure for the turbine?
I'm not sure if I really got what you mean. Sorry.
Well, they are saying that on land, you have maybe capacity factor less than 30%. And then in the North Sea, they have about 40%. And Equinor is bragging about Hive in Scotland that has more than 50%. But is it a good measure?
Well, I think it is, in the sense that you are spending more time producing. And then you're, how can I say, diluting your costs in more revenues. At least that's the way we are used to think. I think that comes a lot with the Mauritius question in the beginning. We are trained to think on a economical way. That's pretty much what.
But just the tricks. If I have a really big rotor on a very small generator, then I can have almost 90% capacity factor. But it's not good economy. No. Okay. Let me go a little into some details. You are talking in all of your papers about pitch and surge, but I didn't see, it's a very trivial question, but I don't see what is the definition of pitch and surge.
Oh, yeah. Okay, so I normally like to think pitch and surge as the modes that are aligned with the wind, or most in average aligned with the wind. So,
yeah, but surge, I think we agree, is this motion.
Yeah.
But what is pitch?
So pitch would be the vertical motion aligned with the wind.
Pitch is a rotation.
Yes.
About which point?
That's source of many discussions and controversies. I remember to see this discussion actually for a row of ships in FPSOs, and then people try to set a point on like imaginary lines where it would be the rotation, but for floating wind, it's not going. The platform is not going to rotate around the CG. That's sort of idealization, but probably between the CG and the fairleads. But I mean the angle, the pitch angle doesn't depend on the reference. So it's
no. The pitch angle doesn't depend on a reference, but normally we define pitch as rotation about the y-axis. Agree? You have a coordinate system, and pitch is a rotation about that axis.
Yes.
But that is not an eigenmode.
No, definitely not.
And if you are going to compute the natural frequency, then you have to rely on which?
Yes, especially, for example, for the case of a spar, you're going to have a lot of coupling with surge. And that's even more complicated to define, like, let's say, an homogeneous degree of freedom. So I think using the conventional naming for the degrees of freedom that we used for offshore industry might at some point become a bit more problematic.
One should maybe use the term pitch eigenmode.
Yes.
Because it's a rotation about, you can decouple in the two independent modes. And then maybe if you have the slide, the first slide here, well, if I press that one, it relates to somewhat this is from journal paper 1, figure 2. And this, you have started with a pure surge excitation. And well, in one case for low wind velocities, you have this, Marius don't see this if I don't point here. It seems like a very nice decay.
Yeah.
And here you have a more complicated decay curve, and you say here you have a limit cycle.
Yeah, this is coupling pitch.
But yeah, it's coupling to pitch.
Yeah.
So the energy is transferred.
Yes.
And then my question is, no, that is not the right one. Well, it seems like I didn't include that one. Yeah. But is this related to the way you have your mooring system?
Yes.
the coupling terms in stiffness.
Mhm.
And so you could say, well, here it's a limit cycle, it doesn't decay, but what is happening here is transfer of energy.
Yeah.
So then you see that the pitch is really depending on the coupling terms, which again is related to the mooring.
Yeah.
But you have stated that the mooring doesn't mean much to the pitch.
Well, I said that the mooring doesn't mean much the changes in pitch period that we saw in the effects, but there's a lot like in the coupling between surge. That's
So
for sure.
that depends on where you are attached your mooring lines, maybe.
Yeah.
And maybe those designing, for instance, the spar here has been very clever in attaching the mooring lines close to the point of minimum rotation and movement. Yeah. So if you have put a different place, it would have looked different.
Exactly.
Okay. Let me see. I should not use too much time. Yeah, you refer to a paper that has become famous from 2019 from Beers and all at the NRL in Colorado. And they state 3 main challenges in the wind industry. It's not only offshore, it's also on land. And they say deeper understanding of the physics of the atmospheric flow. Second, science and engineering of the largest dynamic rotating machines in the world. Wind turbines are that. And then encompass optimization and control of fleets of wind plants working within an electrical grid. The last one we haven't discussed here. You have focused on the second one, but you have also been touching the first one. And my question is, how important is that to your conclusions? And that is just to take this as an example. This is a standard wind spectrum used in industry, the Kaimal spectrum. And in contrary to wave spectrum, these are not decaying to zero for low frequencies. They're continuously up here. And first of all, we don't know very much about this. And secondly is my question, how important is this region for what you see in your computation?
Well, I think the most important regions of the spectrum are the ones that match the natural frequency of the system. So, for example, we would
Then we
have
are here.
surge more or less here,
Yeah.
and the pitch around here.
Yeah.
So now, yeah, this part I wouldn't expect it to excite the system that much. But if we think, maybe if you think in shared mooring systems, like when you go to a wind farm, you might end up with some natural periods that are more to this region. That's what I can
that's a good
think
point.
on. Yeah.
And we see also that when you compute standard deviation of the wind, it will probably increase the longer time history you get, because you get more and more low frequency content. And it's not easy to really say what is
Turbulence density.
now. Right. Yeah. Let me see here. Yeah, and you mentioned the keyword turbulence intensity, and this is from a recent work in our department. And you see, you have used in the order of in some of your simulation in the order of 14% turbulence intensity, and
40-15, maybe.
And these are measurements from a southern North Sea FINO1 platform, and you see. Well, you don't see that kind of turbulence intensities, except for very low wind speeds.
Yeah.
And another thing that is very important, I think, is to separate the different atmospheric stability conditions here. So yeah.
Yeah. Yes, I mean, I normally lean in these IC standards, and I think they are way too conservative for offshore wind, actually.
Yeah, and this also couples to the coherence model you are using, because you are using the standard coherence model.
Yeah.
But have you seen different ways of handling that? Because again, measurements show that you can have even negative coherence. The way it's defined is the absolute value, but it can be negative, and that means that the wind is out of phase on the two sides of the rotor, and that can have some implications.
Of course. Yeah.
Okay, you do some very interesting investigation on what is important to the change of period and also dynamic response, and you mention the aerodynamics and the controller and the nonlinear stiffness of your mooring system.
Yes.
And I think you identified the nonlinear mooring very fine. I come back to that a little. And the controller also you have studied very carefully. So there's a lot of issues there, but it's obvious that the controller is important. But do you think the aerodynamics is important? And then I mean the kind of transient dynamics described by Theodorsen or Küssner and Wagner, these kind of things. Do you think that is important?
It's probably important, but I mean the simulations that I used in that paper and also the tests that I reported this changing period first, I think they're all assume this use BM.
Yeah.
So I mean this changes in period, I don't think they were observed for these more sophisticated models. But how could it be? Well, I don't know the time scale of a transient when it comes to aerodynamics of wind turbines, but if they are interacting with typical natural periods in pitch, that could be an issue. Yeah.
Do you think that is what is the appropriate time scale for having some effect of transients or
well,
do you have an idea of that?
Like on a pitch period of 30 seconds.
Yeah, but from the aerodynamic point of view,
I don't know.
I can mention it's the typically time scale is the time the mean flow takes from leading edge to following edge to trailing edge.
Makes sense.
It's a kind of non-dimensional time you can use, and I think when you compare that to the kind of periods you have, it cannot matter.
Yeah.
So I would say that unless otherwise people convince me about something else, I would say the aerodynamics for the pitch and surge doesn't mean anything.
Yeah, so BM is still good enough.
Yeah, that's another question. Is BM good enough when you also are talking about dynamic loads in the 3P kind of frequency? That's another question.
Yes, I think so. So the 3P, I think the most important is first to have a good spatial distribution of the wind flow. So both the disturbance caused by the tower and also the spatial distribution of the turbulent wind itself. But then, yeah, so where BM could be a problem is that BM assumes that the aerodynamics are quasi-static. So if you had a system, so I'm just trying to think on frequency ranges here. So for example, 5 megawatt wind turbine, the 3P is 0.3 hertz, which is not so low actually.
Oh.
Yeah, then I'd be a bit more careful in saying that BM is good enough actually. Yeah.
No, I agree with your concern that we have using this beam element momentum technique in all kind of standard codes, and all transients effect and all 3D effects are corrections.
Yes, exactly.
Because it's based on 2D stationary flow, and my suggestion, or at least advice, is to do something better. Yeah. Then you showed these different behaviors for the period change.
Yes.
For your system. Let me just see if I had the other. Yeah, this one. You showed that for pitch, they all had a similar change in period when you are crossing rated wind speed.
Yes.
But in surge, you had something different here.
Yeah.
For this semi. And you are making some reflection about that, but my question is really the semi is the red one here.
Yeah, the one with different patterns is the red one, yeah.
But they are all working on this part. They have their equilibrium position at the crosses.
Yes.
And if you have put the wind in the opposite direction, you will have been down here.
Yeah.
And the yellow curve would be extremely much stiffer.
Yes.
The blue one also, but not the red one.
Yeah.
So is this behavior related to simply that you have the wind in the opposite direction?
In a way, yes, because I mean, again, when I presented now, I said that like the CSC or the OC4 is the one with two lines at the fore. But I mean, what's fore and after for wind turbine? Yeah.
No.
Yeah, so I mean, it has a lot to do with like the.
Did you check it in opposite direction?
No, I didn't.
No.
No. But yeah, I mean, here I think what's more like relevant to see is that if you take the second derivative, the curves, the red, the yellow one's the only one that has a negative second derivative. But I don't know how that would actually affect the dynamics, to be honest. But it's definitely
you are linearizing the stiffness, isn't it?
Yes.
So you're only using the gradient here.
Yeah, yeah. But yeah, it's true. Here it's much stiffer. So
yeah,
chances are you would see very short periods there, and you would see the variation. Yeah,
and that also that goes to these equations. When your linearized model up here, then I have two questions, and the first one related to what we just saw is when you construct the mooring line stiffness, you only include the horizontal stiffness of the mooring line in all terms here.
Yes.
But there is also a contribution from the vertical to the pitch. And when you, not maybe for the spar, but that's the point. Yeah. For the spar, that doesn't matter.
No.
But what about the semi?
For the semi matters, yeah.
Yeah. So maybe you should, oops. So maybe you should include the vertical as well here.
Yeah, well, for other problems that I remember, this vertical component in the pitch, we're starting from mooring for semis. It only starts to matter when you have actually very large pretension, which is not really what we normally see in typical systems.
Yeah, no, I'm not quite sure. I don't know the numerical values, but because you are looking for changes in the period.
Yeah, exactly. Yeah,
and that can give a plus and minus, and maybe it cancels each other or something.
Especially if you consider that like the changes in periods are related to the offsets. With the offsets, the angles of these vertical components are completely different. So that could be.
And also the set for the semi is a small value.
Yes.
Yes. So, okay. And then I was wondering, we didn't discuss it. Why are these zero?
Well, I think cross damping terms is a lot of a challenge to
it's a challenge, yes. But they are not zero.
No, yeah. No.
Now it's not trivial to include them, but maybe it deserves some discussion what to do.
Yeah.
Because they can give something. Okay, I think Yeah, I should not discuss very much more, but one question about the controller.
Yes.
In your final analysis, I think it was, and let me see. I think it must be in the last paper. While you are discussing a lot about this, simply moving the filter frequency. So the traditional approach, moving the filter frequency so you avoid resonances. And I agree that is no good solution, but it's very simple to implement.
Yeah, it's adequate for academic research.
Yeah, well, I'm not quite sure. Maybe you get some wrong conclusions. But when you use your more advanced controller, you say that you use a controller natural frequency of 0.31 hertz.
Yes.
No, not hertz, but radians per second.
Yes.
Yeah. And then you say that you use a filter cutoff, and I think that is the same as the corner frequency.
For the nacelle velocity.
For the corner frequency or the filter.
Yes, but the filter in the nacelle velocity.
Yeah. But that's the same frequency.
Yes, but there is another thing, because so the controller frequency is the one that's governing the dynamics of the rotor.
Yeah.
So this filter that I use is actually the filter for that when you measure the nacelle velocity, and you're actually adding a term at the reference that's just a constant times the velocity of the nacelle. If you don't filter it, then you're going to feed the wave frequency to the controller. But that's not actually filtering the rotor speed error. So we're talking about two different things. One,
I agree. Yeah.
One is what you're feeding to the controller in addition to the feedback of the rotor speed error, and the other is the.
But my point is that if you use a corner frequency, which is the same as the controller frequency, will you not then add too much phase shift into your controller?
We do. But then that's why we have to proceed to the stability analysis.
Yeah. But couldn't you mitigate that by a different filter frequency?
Well, I think if I was going to install it in a real wind turbine, I would probably even avoid a classical filter and go for example, observer. But I don't even have the problem. I can just filter out, estimate like a very clean low frequency motion and use that. But I mean, for this purpose, I mean, if you're talking about academic research and using a controller that's better than the detune, I think if we can show stability in that way, which I think it's relatively simple, it's good enough, maybe.
So a practical question, the Roscoe controller makes it possible to implement this?
No, I had to change a little bit because the Roscoe has the feedback controller. And actually the reason for this entire chapter 3 in the thesis is that when I was running the simulations for the 20 megawatts for the first time, I used this feedback strategy. Yeah. And the turbine started to.
Okay.
So then I had to spend some time checking these different approaches and
we have more people that have seen that.
So so just summarizing, I had to implement a small change in the Roscoe controller that allowed me to use the feed forward.
Okay, and then just a last question. In further work, you say that the possibility should be verified for floating wind turbines concept susceptible to instability using numerical methods able to represent nonlinear hydrostatic restoring or model test. And that is in the context of Mathieu instability.
Yeah.
But you say you need a program being able to handle nonlinear hydrostatics. Is that needed for having Mathieu instability?
No, I mean, I think the reason I mentioned Mathieu stability in the further future work is that if you have a period change, like in pitch, that makes it in combination with his susceptible to have Mathieu instability, then I think you might see it without even having this nonlinear hydrostatics.
Yeah, that's my point. You don't need nonlinear hydrostatics.
No, but because then you have like the role that would be played by nonlinear hydrostatics being played by the interaction with the controller.
Yeah. So it seems here that to observe Mathieu instability, you need a nonlinear vertical free surface. But okay, then I agree. Okay, thank you. I think I'll stop there.
All right, thank you very much, Carlos. Thank you very much for this. So now we move to second argument of Paulo. Since you're online and you say the mouse is yours.
And I'll try to stay away from the camera.
Okay, thank you. Thank you very much. Can you hear me?
Yes.
Okay. So first of all, I would like to thank Carlos for the substantial amount of interesting results that he has shown both in this presentation, but especially in the thesis and the shared publicly with the rest of the community through the interesting papers. I can tell you that you have already, I mean, here you have one admirer. There's one PhD of mine that is saying, "Oh, I like very much the papers by Carlos. They're quite clear, interesting." I would like also to highlight the fact that you also addressed a number of challenges and unanswered questions that are not necessarily strictly related to each other. So you had to stretch yourself over a number of challenging and complicated concepts. So this is a testament to your capability, I suppose, and your effort in doing this work. So first of all, thank you very much for this. And I have a series of questions. Obviously, we have seen the thesis before, and we have already asked you a few questions, and you have answered them well. I would like to ask a few questions about some points in the presentation, if you don't mind. So if you can load up again your presentation, and I can refer to a slide number. So is it possible to load again the presentation?
Yeah, we're in
Okay.
the process.
Okay, thanks. And could you please go to slide number 37?
Yeah.
And I'm seeing the camera with the whole room and not with you. So maybe it's better.
Yeah, so I'm trying. Yeah. Can you see me now? Or?
Yeah, I can see you, but I think it's important also to see the slide. Oh, okay. Okay, so thanks. Extreme value analysis. Obviously, you explained that that's relevant for those extreme loads that can lead to problem with plasticity, buckling, and limit motion amplitudes. And basically, what you do, you run a series of analyses, and then you try to infer from these series of analyses what is the extreme value distribution. So to do that, I suppose what you can do is, in this particular case, you have time domain simulation for short-term conditions, and you mentioned 20 seeds. Now I would like to know, there is an about 20 seeds, around 20 seeds there, but what is the justification behind 20 seeds rather than 15 or 30 or 100?
Yes. Normally, literature speaks on about 20 seeds. I think the correct way to do is to run, as I said, 15, 20, 30, at least for a few cases, and see if the extremes that you get from them converge. But the whole idea is to have enough representativity, because if you only have one value from each realization, then you won't build a good tail for the distribution with only 5 or maybe even 10 seeds.
Mm-hmm. So it's the key is really mentioning a kind of a sensitivity analysis of the extreme value with respect to the number of seeds.
Yes.
You mentioned here that the extreme value distribution that you obtain from the measurements of the maxima in your simulation can be fitted to Gumbel distribution. But is this the only distribution that you can adopt?
Normally, for extreme analysis, we end up with three, which would be Gumbel, Weibull, and Fréchet. Fréchet is not really relevant for this sort of applications, but normally Gumbel and Weibull. But Gumbel tends to be the one that fits better for most marine applications. Again, that would be, I mean, I didn't do that, but that would be the case to try also Weibull and see which of them would really fit better the instrument. Yeah.
But isn't there a generalized distribution that can capture and represent in a continuous way Gumbel, Weibull, and Fréchet?
The generalized distribution actually is either one of the three, if I'm not wrong. So when you try to fit them with some algorithms, what they do is give you a parameter, and this parameter, according to if it's smaller than one or bigger than one or something like that, I don't remember, it will indicate whether it is Gumbel or Weibull or Fréchet, isn't it?
Well, I think it's a bit more than that, but in any case, wouldn't be better to use directly the generalized extreme value distribution and let the data decide if it is a Weibull or it is other types of distributions?
Yeah, it's probably better not to stick to one from the beginning. That's for sure. Yeah.
Okay. And when you use this kind of distribution, Gumbel, Weibull, or generalized extreme values, you tend to identify the maxima by just saying, okay, I do X simulation, I pick the maximum value of the interesting parameter for each one of these simulations. So it's a kind of a block maxima approach where you identify one maximum for each simulation. Do you know any other method that?
Yes, there's one that was, I know the picks our threshold, but one that I used before in other contexts was this one that you assume the maxima as governed by a Poisson distribution, and then you get more data from each realization. So then you don't have to really run that many realizations. So this was the one that was developed by Arvid Nas some years ago with another student. It's called Nas Gaidai, and there's also the Acer method. The Acer method I just read about it but never used it.
Okay.
They're of course valid approach to avoid these many simulations. They're more rational in a way.
Yeah, it can be a valid point in terms of especially you have touched upon design, also large wind turbines, and then whenever you talk about design, you in theory should consider a large amount of load cases and realization of these load cases with different seeds. So the other argument is that at physics level, whenever you do one simulation and you pick the maximum, and then you do another simulation and you pick another maximum, what is the justification behind the fact that you are giving the same importance to the maximum in one simulation to the maximum in the other simulation, while maybe from an extreme point of view, you have two maxima in the first simulation that are more important than the maximum in the second simulation. So that is where you start to think about, or maybe there is a peak over threshold and having that is. So again, I'm not saying that you can always do more, and myself, I for limitation of time and resources, I don't do all this, but it would be interesting to see how things change when you start to think about a peak over threshold and maybe a Pareto or a generalized Pareto distribution, and how these will affect the extreme values.
Yes.
can we go to slide number 41, please? I know that Finn already touched upon that, but there is a lot of interesting information in that one. So slide number 41, you can, in the bottom, you show how the natural periods, the periods of oscillation coming from the free decay test in surge change when you change the wind speed.
Yes.
And in the paper, you observe the fact that qualitatively you have that for the OC3I wind platform, as well as the CSC 5 megawatts platform, if we go from the left to the right, so for an increasing wind speed, the period that you observe increases and then decreases, while for the OC4 semi-submersible, it decreases and then increases. Now, again, you touched briefly upon this in the paper, but I wanted to know if you reflected a bit more on why you have an opposite behavior on the OC4 with respect to the other two platforms.
Can you repeat the finish, please?
So why you have an opposite trend between the OC4 and the other two platforms? So why for one is augmenting then diminishing, and then for the OC4 is diminishing and then augmenting?
Yes, so as we discussed now with Gunnar, for the first two cases, for the OC3 and CSC, so when the wind is blowing in with 0 degrees incidence, the turbine is being pushed towards two lines, while for the OC4, it's pushing towards one line, and that has an effect on the way the stiffness, the way the linear stiffness changes for each of the displaced points. Because when you linearize, you end up with different inclinations in these curves that you see in the plot. So, and as Figurna said, should I use 180 degrees to the wind, I would probably not have seen that. So that's pretty much because of the direction of the wind combined with the number of lines that you have.
Well, that may be, but it's still not clear to me how would that would explain an opposite trend. I mean, if we stick to a very simple approach, let's say 1 degree of freedom surge, and how can you estimate rule of thumb what is the natural frequency in surge?
Yes. In the way that I did in this work, I first fit a polynomial to these curves, and then I linearize this polynomial around these offset positions. And yes, I mean, I didn't really stick too much to the physics of this. No,
well, let's keep it simple. So the 1 degree of freedom approximated formula for the natural periods is the square root of K or C, that is the stiffness, right? Divided by the mass plus the added mass. Very simple. So if these natural periods changes can be due at this simple level to either or stiffness, mass, or added mass. Now, I don't think the mass changes when you change the wind speed, so we can exclude that. The added mass is interesting, but for the time being, let's keep it apart and say, okay, it's not the added mass that changes with the wind speed. So we comes to the same conclusion that you came, that it is the stiffness coefficient that changes. When you change the wind speed, the platform will be displaced by a certain amount depending on the thrust force, and therefore you will be in a different displacement point, as you show in this graph on the top right. And there, the stiffness coefficient, that can be the stiffness coefficient at the end of the day is the slope of that curve, isn't it?
I didn't get the end. It's a bit.
Sorry, we came to the point that the change in natural period is probably due to the change in stiffness coefficient in this simple formula of square root k over a plus m. So now, if I ask you, what does represent the stiffness coefficient in your graph where you have force versus displacement?
Okay. Let me think a bit. So, okay, so if you think that force would be the stiffness times the displacement, so then the slope of the curves would represent the linearized stiffness.
And that's exactly that. So
Yeah.
the slope of the curve is representing your C. Now, taking into account the simplified approach and discussion that we just did, the fact that the natural period is augmenting, or equivalently, the natural frequency is diminishing, it means that in this simplified approach, you should have the slope of the curve that diminishes with augmenting the wind speed.
Yes, but I mean, the period, you said that it's the proportional to the square root of mass over k, but it's actually k over mass, but it's actually the period is 2 pi square root of m over k. The frequency.
Yeah, sorry, I meant the frequency is square root of k over a plus m. So let's take the period then. The period is the opposite, so it's 2 pi square root of a plus m over k. Okay.
Yeah.
So if your period is augmenting, that means that your k is diminishing, right?
Yes.
So k, we established that is the slope of the curve, and basically what should happen in this graph is that when you move toward the right, so for larger displacement, that means we have to say from cutting to rated wind speed, we are moving toward larger and larger displacement, so toward the right.
Yeah.
Your k should be diminishing, but from this graph, it seems that is augmenting, not diminishing the slope.
Yeah, but actually, when you are subject to wind, the wind turbine is going to the negative x direction, isn't it? Or let me think. Sorry. No, it's correct. It's going to positive. Sorry. Yeah. So let's see. For the blue curve for the OC3, if you compare the 0 with 30, for example, so apparently you have a larger slope at 30 than at 0, which means that would have a shorter period for 30 than at 0, and that's what you see in the plot, right? So at 30 meters in this plot at the right, I try to find the pointer here. Yeah, here. So here the slope is bigger than here.
Yes.
Agree? So the k is bigger here than here, and that is consistent with the period being bigger. Oh no, sorry.
The period should be smaller.
Yes. Yeah, but then I mean, no, just I have to think. Yes, I'm quite confused now, I have to say. So these points that you see, the stars, they are the rated wind speed, right?
Yes.
So here is where we are at 11.4 meters per second, which is when you have the biggest, the longest period for the OC3 and CSC. Okay. So, which means that we should have here, so the lowest stiffness.
More than lower, lower.
Yeah, I have to say that it's a bit difficult to talk about this slope here. I mean, I can't say like visually if the slope here is bigger than at 0, to be honest.
Yeah, I suppose what would help would be to plot, as you did force versus displacement, maybe plot the derivative of the force versus displacement, because again, it's not easy to see from this graph. My gut feeling is that from 0 until the displacement for rated, your curve is actually concave, so it is like this. While from the point of displacement of rated wind speed to larger displacement, the curvature is on the other way, is convex.
Yeah.
So that would explain the fact that up to rated wind speed, the slope of these things is diminishing for OC3 and CSC, and therefore you have larger periods, while it is augmenting for the OC4, and therefore you have lower periods. So it's a matter of basically representing a similar plot, but rather than the force versus displacement, you can have the stiffness versus displacement, the linearized stiffness versus displacement.
Yeah, that makes sense actually. Yeah.
Okay, sorry but I think
No, it's very
you are
interesting.
an advocate of simpler approaches to understand complex behaviors, and I completely agree with you, and I like frequency approach. So I think it's important to go back to the basics and those very simple formulas that can explain a lot.
Yeah, and in this case, it's also going back in time, because this paper was published a few years ago. But okay, yeah.
Can we go to slide 49, please?
Yes, 49.
So in this slide, you're showing basically again how these periods change in surge and in pitch, and comparing what you obtain with your simplified approach, the 2 degrees of freedom, against the value that you obtained with the aero-hydro-servoelastic coupled model of dynamics, that is SIMO or SIMO plus reflex. And I was quite pleased by the fact that they actually are quite close, considering how much more advanced and complicated is SIMA with respect to a 2 degrees of freedom model. So again, it's a good point toward simpler approaches to understand the physics underpinning the phenomenon. Anyway, you, as far as surge is concerned, and as far as the OC3 is concerned, you rightfully observed that with the SIMA, you have a kind of dip, or a depression, you call it, between 8 and 10, 8 and 11, let's say, meter per second. Your SIMA shows a period that is consistently lower than, even if by a little bit, not that much, but there is a different trend, basically.
Yeah.
And you mentioned that this could be due to the fact that the dynamic of the rotor is not included. Can you expand a bit on that possible explanation?
Okay, you mean here in the pitch curves, you mean?
No, the surge. The surge
surge, yeah, I think what I wrote in the paper was that, like, for this difference that we see in the pitch curves, we see these depressions here, that I think they are because of not including the rotor dynamics, because here I got the coefficients with these forced oscillations, where the nacelle is not being affected by the rotor dynamics, but it's affecting the rotor dynamics. So then I would have an incomplete representation effect here. But here for this part of the curve, I remember that I struggled a lot to understand, and I didn't really realize why you have this such sudden increase here in this curve. Or it seems it's not really a sudden reason of the curve, but actually for this wind speeds closer to rated, for some reason here the period was more or less flat. But for surge, I don't think we can explain with the water dynamics, no. And I don't know why I saw this, to be honest.
have you done any further investigation on what could be the cause of these, or can you think about some effects maybe that pop up in your mind later on?
Well, one thing that we cannot neglect is the possibility that the method that I use to count the cycles might be wrong somehow. Because if you see the right curve is basically what you get by linearizing the marine stiffness and calculating the G values. So that's, and when you do that, you have a curve that is more credible, like it follows the trend that it should follow. So one possibility is that the way I counted the cycles was a bit ill there, because close to rated, as I said, this added inertia due to aerodynamics, it doesn't really affect the period in search, but the damping can affect. So I suspect, I mean, if I would come back to this problem today, I would start from there. So trying to check if I find a better way to count the cycles and calculate the period. That's the only thing that I can think here, but it's really strange. I mean, it's not a small difference. So like from what I would expect to be to what it is, it's like 2-3 seconds. So yeah.
Yeah, and also due to the fact that there must be some uncertainty based on what you measure and how you measure things.
Yeah.
But I think that would give a kind of a systematic error throughout the wind velocity, wouldn't it? You have a very good match beyond the rated wind speed, and you seem to have a increasingly worse match below rated wind speed as you augment the wind speed.
Yes, unless you had, for some reason, for example, no, let me think. Yes, no, that's true. I mean, if you had some problem in the counting of the cycles, it would affect the rest. So yeah, I'm trying to think like what could be affecting only the near rated condition, but that's strange because there the controller, yeah, what could be is maybe the controller is entering and getting out of the rated region there, and then you have some difference in what you see in the cycles. That's a possibility. So, but then again, why it doesn't happen to the other platforms, that I don't know.
Okay,
that's the only thing that I can think, because when you are close to rated, you start to see these strange on-off effects with the controller that can be a bit complicated to understand.
Okay. Well, it's obviously when we do a paper, all of us, we discover one thing and we create 4 questions, and we cannot go factorially into this all the time. I have another question, page 62, sorry, slide 62. Okay, so here you're presenting your parametric design or parametric approach that you have adopted in order to investigate a design space of floating superstructure of the spar type, varying systematically these parameters, geometrical parameters. And then you talk about some constraints that you have adopted in order not to end up with unpractical or unfeasible designs. Now, obviously, the first question is, you adopted a simplified approach, and there's nothing wrong with that at this stage, in terms of a cylindrical hollow structure with constant thickness, so no girder or of the sort. You have one, we can call it an equivalent constant thickness of 60 millimeter. Now, where is coming from this value?
The thickness came, actually, I just used the same as a previous PhD student that worked with spars using his thesis. So I only took that as a representative value for the thickness.
I'm afraid at PhD level, this is not an acceptable answer. You need to know the rationale behind that, why it took 60 millimeter.
Yeah, so yeah, that's the thing. I mean, I took action from a paper that he published, so it's But I mean, I don't have a better way to defend this choice. I just used what I saw before and as a representative value for both the weight and for structural capacity.
Okay, then well, I think it's important because if this was just another parameter that you needed to estimate some secondary parameters or results, that's okay. But as far as I remember, that you do some fatigue evaluation as well. So obviously, the constant thickness or the thickness value may have some importance into that. Again, there's nothing wrong in adopting a simplified approach. Nothing wrong with adopting a similar value to the previous, the guy before you, especially if it is from a peer-reviewed international paper. But again, it's important to realize what are the consequences if you vary 60 to 70 or to 50 and then for the results of your work. And then I was also curious about the constraints on the periods. For example, the period in surge, 120 seconds. It is true that typically spars have periods in surge that are larger than 100 seconds, 120 seconds. But why did you constrain it to be 120 and not larger than a certain amount?
Yeah, well, if I'm not wrong, 120 is what we have for the OC3, high wind.
Mm-hmm.
Yeah, it could be larger, but then there's a problem because the spars, they will have different masses. They do have significantly different mass. You can see here, for example, where's the mass, total mass, steel mass for ballast mass is very different. So if you allow the period to be longer, then you could end up with stiffnesses in surge that would be way too different from each of the spars, and that would make the comparison a bit less fair, perhaps. But
it's fair with respect to which parameter?
Because I mean, I was really interested in comparing the three spars, right?
Mm-hmm.
So if you have the same period for the three, then you're subjecting them to the same, not the same stiffness because the masses are different, so the stiffness are different. But then you end up with heavier marine systems for those that require more stiffness, and that's something that I think is fair to have in the comparison. If you just had a constraint there saying, okay, it has to be more than 120 seconds, I think that, for example, mass of the marine system wouldn't be as a fair comparison as we had here. But to be honest, the stiffness for the marine system, it should be primarily linked to allowed excursion, of course. And then you would have this more inequality constraint than just sticking to 120 seconds. That said, this constraint of 120 seconds was not very strict, actually. I just started from there. And then the algorithm that I used to run this parametric analysis just goes iterating until it gets to something close to 120. So if you see the period, it's actually is a bit longer for spar 6 and it reduced for the others. So it's not so strict, actually.
Okay. When you talked about that period being kept around 120,
yeah,
I thought of a similar answer that you provided, but more precisely, I mean, at the end of the day, the surge period, it's a kind of a measurement of which range of periods of frequencies the platform will be more susceptible to external loads in the surge degrees of freedom. So if you want to capture different platform, but that suffers more or less from the same, to the same extent from exciting forces in surge, then you kind of say, okay, in surge, this platform have similar dynamics because I can say that they become kind of resonant around 120 seconds. So that would kind of, for example, going back to the first paper, will give you a kind of a similar behavior in terms of change of dynamics from a mooring stiffness point of view when you change the displacement. But again, okay, I had a similar question, for example, for the yaw degrees of freedom. Why exactly 16 seconds?
Yeah. So for y'all, I was only worried about escaping excitation at 1P. That was the only requirement.
Okay.
So 16 escapes for all the cases.
Because again, the other degree, the other constraints of having a heave period larger than 25 is something more common to say, okay, as long as it is above this amount, it's okay. The larger, the better, but 25 is a good amount. Well, I think I've taken a lot of time already, so I'll stop here, but thank you very much for the discussion.
All right, thank you very much for this. Thank you to the committee and the audience. The committee will have a meeting, and hopefully we are back about 4 o'clock. We will meet down. So we'll have meet down. I think those are online, or so perhaps they can join and see the celebration. We'll have a gathering down. So see you about 4 o'clock.
So everything down.
Yes.
Yeah. Okay. Thank you. That's quite quick, actually. Yeah.
It's not as painful as
I think I spent my entire PhD waiting for suffering design, and that was okay. Yeah, that was very tricky. I mean, I would never expect it. The floor, yeah. Yeah, I can just, I don't think I need the box. So.
so they don't have to run away with your microphone.
Oh yeah, good idea.